All right, last time we started section 3.6. Who can tell me what optimization means? And just a general description of what it is. Don't everybody talk at once. What does it mean to optimize something? What does that mean? Snyder.
To use calculus to find solutions to real-life problems.
Okay. We are going to use calculus. There are ways to optimize without calculus. We're going to be using calculus. Real-life problems, what kind of real-life problems specifically?
If you want to find the minimum amount of fence you need to close an area.
Okay, so finding things like minimum or maximum. Okay, so optimization problems are all about finding something's best ability to do something, right? At its optimal value. And that's exactly what we used it for last time, was about a fence, right? Fence alongside a river. So that's the one that you're remembering was this particular problem. So we had this river and the fence along it, and we wanted to minimize perimeter in this problem. Does everybody remember that? All right. Okay, we're going to do a couple more examples of optimizations, places where we're maximizing or minimizing something. We're going to do number 2 over here. Just a reminder real quick. Things about optimization, we want to look for a sketch if we need to draw one. Identifying what we know versus what we don't know. Equations that relate those quantities together and getting them in terms of one variable. We actually had to make sure we were careful to do that on the last problem. And then determining maximum and minimum allowable values. That one's something that's really easy to forget to do, step number 4. So try and remember that one, because otherwise you might end up with an answer that doesn't make sense in the context of your problem if you're not being careful. And then the last one's the one that really involves the calculus, which is actually using calculus, in particular derivatives, to find maximum and minimum values. All right, so let's take a look at our second example. This is a very classic. Do you know what classic means? Somebody says it's a classic problem. It means everybody loves to use it. It's a really good example. Really good example of maximizing and minimizing something. So we have a piece of cardboard, and we're going to make a box out of that cardboard. The cardboard original size is 6 inches by 10 inches. And it says what we're going to do is we're going to cut an x-inch square, of length x on each side, out of each corner, and then we're going to fold the box up. So if you can picture that, this isn't an 8 or 6 by 10 sheet of paper, but imagine this is your sheet of paper, all right? And you're going to take each of these and you're going to cut out a corner from each of the sides of the box, right? Each of the corners is going to be cut out. And then you're going to fold along the cuts. So when you fold, you actually end up with something that looks like a shoe box or a shirt box or something like that. Does everybody picture what's going on? It will help us if you've got the picture in your mind. Awesome. Okay, and then the question is, of course, how much volume? What is the maximum volume or the dimensions of the box or something like that? This one says they want us to find the actual amount we have to cut out at each corner to make this the maximum volume. All right, so what's my first step in this problem? Yeah, I mean, this is just aching for a picture to be drawn, isn't it? I mean, like I grabbed a sheet of paper and I'm playing with it in front of you, right? A picture is very appropriate here. So we're going to draw a picture, and what is my picture first going to look like? What shape? Rectangle, you bet. Rectangle, that's not what I want. Hang on, let me try that again. All right. All right, so here's a rectangle. I do know that the rectangle is a 6 by 10, so I'm going to write those in right now because I might need them later, and it's information that I know. And then what am I going to do with my rectangle?
Are those inches?
It is in inches. The little notes right here where they put those 2 little dots, or 2 little apostrophes, mean inches. Yep, we're going to do it in inches on this one. All right, so what am I going to do next with my picture? What's it say? I need to cut out the corners, right? All right, so I'm going to make little boxes, and they should be all the same size. I'm going to do my best to make them look like they're the same size. But we're going to make little boxes in each one of the corners that are going to represent what we're cutting out. So something like that. Okay, that's my cutout. You know, cut along the dotted line kind of thing. It's not perfect, but it's at least somewhat reasonable. Is that okay? There's my cut along the box, my corners of the boxes. So now I don't really have a rectangle anymore, right? I've got this funny shape with extra little cutouts. And then what am I going to do with the actual sheet that I still have left? I'm going to fold it, all right? So I'm going to fold along it. So let me draw my fold lines in next. In fact, I'll do it in a different color just to make that clear. So these pieces are ones where I'm going to fold along. Okay, so we're cutting out the black squares in the corners. We're folding along the red lines. And the shape that we have left is going to be having a volume, right? Because it says that I'm going to maximize the volume. It was right here. I've got my 6 written on top of it. Let me move my 6. It says I want to maximize the volume. Okay, so I need to know the volume of this shape now. It didn't have volume originally because it was just a sheet of paper. But once I fold it, it's going to have volume, space inside. So how do I find the volume of a shape like this? Yeah, you guys are remembering it well. Length times width times height. Let me make one more note in my picture. I'm going to write in here my x, because it told me my sides were side length x that I'm cutting out of each corner, right? Fantastic. All right, I need to know the length, width, and height of this box. I'm going to do the hard one, the height. It's x. That's not the hard one, right? Does everybody see why the height's x? I'm folding up the corners. And when I fold up each of the corners, I fold them sort of out of the board that you're looking at. That's the height of my box. So the height of my box is actually x. Length and width are not 6 and 10. That was the 6 and the 10 of the original sheet of paper. They're not 6 and 10, but what are they?
6 minus 2x.
Good job. 6 minus 2x is one of them. What's the other one going to be? 10 minus 2x.
Why do you have the x's where they are?
It told me in the description that I'm going to cut x-inch squares out of each corner. So each of these corners, the length and the width of that square is x. I don't know what it is yet. That's what I'm going to try and find out, actually. It does have a numerical value, but it is represented right now by the letter x. Now, tell me why in the world I have 6 minus 2x and 10 minus 2x. Those are the right values, but where did they come from?
6 by 10.
Okay, it was a 6. So let's talk with me about the 6 one, Alexa. The top is 6, right? So where does the 6 minus 2x come from?
Because you cut 2 x's out.
Right, so it's actually the length of this piece, right?
Yeah.
Right, so it's like we're looking at just the bottom rectangle of the box itself. And it was 6 inches along what I've got listed, so my drawing along the top and along the bottom of my picture on the screen. But I've cut an X out of each corner, so I've got X's on a little bit less on each side now by X. So this piece right here is 6 minus 2X, and it's 2X because I had 2 X's that are reduced by. And then this piece, of course, for the exact same reason, is the 10 minus 2X, right? Is everybody good with that? Okay. And it makes sense that the corners have to be cut out squares, because if they weren't, then we'd be folding it up and we would have sort of one height of our box different than the other height, and that wouldn't work, right? So it really does make sense that we're cutting squares out of the corners as well. All right, so the cool thing is that unlike the last problem that we did, I don't know if you remember it or not specifically, but we actually had to work a little bit at figuring out how to eliminate variables so that there was only one variable on the right-hand side. And the cool thing right here is it's already in one variable on the right-hand side, isn't it? It's just x's. Okay. Before we forget it, what's the step I said is the easiest one to forget, practically speaking? The max and the min values, like realistically in terms of my problem. So tell me what the minimum value that is at x would be. X has to be bigger than 0. We can't cut out a negative square on the corner. We can't even cut out a 0 on the corner, right? So x is clearly bigger than 0. X is also very clearly less than something. What would it have to be less than? More. It can't even be that big. Smaller. But smaller than 6. Smaller than 4. No. 2.
6 minus 2x.
The magic value is 3. Okay, Josh saw it now once I told him what it was. Can you explain what you saw, Josh?
Because if you cut out 3 from each side, then you still have nothing.
Yeah, so along the top it's 6 inches long, right? If I cut out 3 from the left and 3 from the right, would I have a box? No, I wouldn't. So I definitely need it less than 3. We could also say less than 5 because that's the length of my box, but 3 is more restrictive than 5. So my value for x is definitely that it's less than 3. And if you want to write this sort of in a one statement, you could say something like this, right? X is between 0 and 3. This is going to be really important in this problem because one of my answers isn't going to fit into this criterion, and if I'm not being careful, I might actually think I got 2 answers out of this when I'm done. So this is a really important step on this particular problem. Sometimes it ends up not being all that crucial, like in the last problem we did, didn't really end up mattering, but sometimes it does end up being really it does really end up mattering. All right, now I've got an equation, and I looked at the maxes and min of what my values can be. Where am I? What do I need to do next? I need to what? I need to do the calculus part of it, right? Okay. I'm going to do one thing before I do the calculus part of it. Any idea what I might want to do? Yeah, I'm going to multiply it out. I'm going to distribute. Because I think that this problem will probably be easier to do with just power rules if I do the algebra first. So if you really want to do this with a product rule, you could. I'd at least distribute the x through somewhere before I did a product rule. But this one's not too bad to just distribute. It's just a binomial by binomial. And we've got that x on the outside. So I'm going to take a look at that one with you in this way. So I've got 6 times 10, that's 60. I've got 6 times negative 2x, that's negative 12x. I have the inside terms, negative 2x times 10, that's negative 20x. And then the last term's negative 2x times negative 2x is positive 4x squared. And then all of that's times x. So I'm going to do 2 steps at once. I'm going to combine the 2 middle terms. What is that going to give me in the middle? Negative 32x, and I'm going to distribute the x at the same time. So I combined a couple of algebra steps. If that's bothersome to you, write them out separately. But I'm going to have 60x minus 32x squared plus 4x cubed. Okay, so I still haven't done any calculus, right? Not yet, but I'm really close. What calculus do I need to do now? I think I heard you say take the derivative, Allison. Is that what you said? Yes. Awesome. What's that? Yes. I was going to rewrite it later in order, but I'd be happy to rewrite it now in order. So Jen would like me to write this as 4x cubed. Okay, provided that the iPad will cooperate. Minus 32x squared plus 60x. So Jen, you might be a mathematician if the order of that bothered you, because it bothers me too. I like to see the decreasing order of exponents. All right, so I was told just a moment ago we need to take a derivative, and I think you guys all agreed with that. And this one's really straightforward to take a derivative of, isn't it? It really is. What's the derivative of this function? Okay, did everybody get that? That's what Snyder told me to do. I think he got it right. Look good? Oh, it was Jacob. I'm sorry. I heard the voice coming from this direction. I apologize. Okay, that looks good to me. All right. What do we do after we take the derivative? We set it equal to 0. What does setting it equal to 0 actually find for us? Critical points. Very good. We want to be careful what we're actually finding. We're finding critical points. Now, as I set that equal to 0, what do you notice about 12, 64, and 60? They're divisible by 4. And if you didn't catch that they were divisible by 4, you should at least catch that they're divisible by 2, right? Because they're all even. So if you don't catch the divisible by 4, divide them by 2, and then you'll see that you need to divide them by 2 again. Okay? So they are, in fact, divisible by 4. So that's actually where I'm going to start. I'm going to reduce everything by dividing by 4. Technically, both sides. That's why I'm allowed to do that. So this is going to be 3x squared minus what? What's 64 divided by 4? It is 16. Good. 16x. And then 60 divided by 4? 15. And, of course, 0 divided by 4 is 0. Excuse me. What would we try to do next? Can't move the 15. We would do that if this equation were linear, but it's quadratic, so moving the 15 won't help us. Factor. We would attempt to factor. So let's attempt to. What do you think? That would give me the 16 in the middle, but the 3 in the front's going to cause a problem with that, right? It's not just x squared, it's 3x squared. So if I were trying to factor, I would guaranteed have to have a 3x and an x here. That's the non-negotiable. And I would guaranteed have to have two negatives, right? Because otherwise I wouldn't get a positive 15 at the end and a negative 16 in the middle. So my options for 15 would be 1 and 15 or 3 and 5. I'm getting lots of heads going like this, back and forth. 1 and 15 don't work. What about 3 and 5? Like this? What's 9 plus 5? It's 14, not 16, right? No, this is our best option, right? Like this is the closest that we're going to get. And it didn't work. So what now? Yeah, it doesn't work. This does not factor. Bummer. Which means we actually have two options. One of them is a quadratic formula. The other one is what? Do you remember? I mean, we're not really going to do it, but somebody said it. At least I thought I heard it. The other option is called completing the square. Do you guys remember that option? It's not like crazy hard or anything. It's just not the one that we usually kind of go to. Quadratic formula is a little bit more natural to us. So this doesn't work, right? Draw yourself a big old X on this. This factoring idea is not going to work on this one. So we are left with the quadratic formula. And so, have we talked about the quadratic formula in class? It seems like I've done it once. What does X equal in the quadratic formula? Just the general one. I agree. Do you guys all agree? Is that good? All right, let's fill that in then with our A, B, and C information. So what is the beginning going to say? What's negative B going to be? 16 plus or minus the square root. What's B squared going to be? Well, it's technically negative 16 squared or even 16 squared since the negative is going to go away. And it is 256, isn't it? I think that's the value that you get when you square that. Minus 4 times A, which is 3, and C, which is 15. Good. All over 2 times what? 2 times 3. All right, so somebody tell me, what do you get underneath the radical before you try to square root? Just the simplified version. What is 16 squared minus 4 times 3 times 15? 76. Awesome. My denominator is a 6. Now, let's pause for a moment and let's just talk through what's the deal. This is a word problem, an application problem, a problem where in the end we're going to say X equals something and it has to make sense in terms of the context of the problem. So, what kind of a number am I wanting to give back as my answer? It's going to be positive, that's true. Something else, though. What's that? It will have to be between 0 and 3. Something else. Let me ask the question differently. If I give my answer in terms of a square root, will that make sense? No. Right? It doesn't make sense with the context of the problem. So this is one of those cases where you have to actually use the context to actually say, you know what, I am going to round to an appropriate decimal number of places because that's what makes sense, right? Most of the time in math, we don't want you to round anything. Agreed? Okay, but when we're talking about a context problem, that's what we have to do, or it doesn't make sense. So what is the square root of 76 as a decimal approximation? Let's go ahead and use 4 decimal places for now, and we'll put it as 2 decimal places when we finish out the whole problem. What'd you get? 8 point what?
7.
I don't even think I have this written down. 8.7. 1.7. Let's go with 4 decimals.
Oh, 7, 8.
7, 8, like this? Okay, does everybody have that part? Okay, now this gives me 2 answers, right? Because I've got a plus something and I've got a minus something, and they both actually happen to be positive, so we don't actually get any negatives on this one. So let's take this and do the 2 answers. I want you to take 16 plus this 8.7178, divide by 6. Somebody tell me that value with 2 decimal places. Final answer, 2 decimal places. What do you get when you add? 4 point what? I don't think it's 24. I think did you divide by 6? Okay, do the division by 6. Okay, 4.12 will give you, I think that's what you'll get, Jacob, if you divide by the 6. Let's do the subtraction. Let's do 16 minus 8.7178, and then divide that by 6. 1.21. Are these both viable answers? No. One of them doesn't work. Why? That value is bigger than 3. That would not give me a box, right? So we really only have one possible answer, and we have to make sure that it really is the answer. Do you remember that from last time? What did we do to try and make sure that an answer really is the answer here? We did a number line. What were we looking for with a number line, Jacob? We were looking to see if it was a minimum or a maximum there, right? So that's one way to do it, is with a sign chart. What's the other way that we could do it? Plug it into what? Not the original. Not the derivative. The second derivative. Yeah, there's 2 tests. There's the first derivative test. That's the number line thing that Jacob mentioned, right? Which is totally fine. You can definitely do that. Another option is to do the second derivative test, which is to take the second derivative and then plug that into the second derivative. I actually kind of like that on this particular one because it's a polynomial, which means taking the second derivative is easy. So that's what I'm going to do on this one. Feel free to do a number line. It doesn't hurt anything. But this one's actually really nice to take a second derivative. What is the second derivative of 60x minus 32 plus 4x cubed? Oh, let me do it from the other version, the one that Jen had me create below, right here, just so it's in order. What's the second derivative going to be? Oh, I didn't mark on the same one. It's still not marking the right thing. Here we go. Here's my second derivative. What I want to take the second derivative of anyway. Yeah. Yes, it's the 12x squared part.
24x minus 60.
24x minus 64. Is everybody good with that?
Wouldn't it be easier to take the second derivative? Okay.
You could take the second derivative of 3x squared minus 16x plus 5. It wouldn't hurt anything. You'll get the same answer either way, you just get smaller values. Yeah. And then we're going to use this, and we're going to plug in the number 1.21. And we're looking to see what about this value? What are we trying to find out?
If it's concave.
We're going to find out about concavity. How do we decide about the concavity? If it's positive, it's what? Concave up, good. Positive, concave up, which means I would have a minimum. And if it's negative, it would be concave down, and I would have a maximum. So we really care about whether it's positive or negative. All right, so tell me, do we get a positive number or a negative number? This is negative. And since it's negative, it would be concave down, and I would have a maximum. So does this, in fact, maximize the volume of the box? It does. Now let's make sure we actually answered the question that was actually asked. The question asked was, find the value that of x that maximizes the volume of the box. Could they ask us what's the volume of the box? They could. They didn't on this one. So we want to be careful we answer what was asked. We want to know the value of x that maximizes the volume of the box. The value is 1.21 what? Inches. And you can feel free to use the little inches notation, which looks like that, or to write out the word inches, or the abbreviation IN. Any of those are fine. Just make sure the units are on there. Because just like Snyder asked at the beginning, is this centimeters or inches? Well, it matters, right? Centimeters are a lot smaller than inches. The answer means something different, so we want to be careful to answer appropriately. All right, we have one more example. Any questions on this one before I move on? Okay. This last one is probably the least application type problem, but it's an interesting application that involves something that is applicable in other contexts as well. So let me show you what I mean. The question says to find the point on the curve of y equal x squared that is closest to the point in the plane 0, 1. Okay. What would we do first? Draw, right? It's just begging for a picture. This is a graph, right? It's a graph of an equation. We're talking about taking a look at how far something is away. So we're going to draw a graph. What is y equal x squared? A parabola, very good. Looks something like this. Oops. 0, 1, where is that? On the y-axis, 1 up, right? About right there. So what I want to do is I want to find the place on the curve that's as close as possible to that blue dot. Tell me what you know about that location. How far away is it? What's the minimum distance it could be away? Or what is the distance that it has to be no further away? I'm sorry, no closer away than. I didn't say that right. Okay, 1 is the most it could be away, right? Because you know that from that blue dot straight down is 1 away. Agreed? You are guaranteed to be 1 away from that value or closer. And actually the same is true if you go left and right as well. When you think about graphing a parabola, I don't know if you guys remember this, but one of the ways to do that is to look at what we call the amplitude of the parabola, the value in front of it. And so we would go over 1 and up 1, and you actually have points on your curve that are at a distance of 1 away on the left and right as well. So we are definitely, the distance that we're talking about here is definitely less than 1. It's also definitely positive, right? I mean, it is not on the curve. The distance is not 0. This point and this curve do not coincide. All right, so the distance is less than definitely less than the value 1. All of these points actually are 1 away from the other one. The one that in question is 0, 1. All right, so what is it that we're wanting to find the maximum or minimum of again? The distance. Yes. Does anybody remember the formula for distance? Okay, so the distance equals, there are some squaring involved. I think I need something else before that, though. It's a square root, right? And then what is it the square root of? Well, you can write it generally speaking first, sure. x2 minus x1 squared. So there's the squarings you were talking about, Akil. Plus, good. Fabulous. Good memory. Okay, does everybody sort of remember that? Maybe back of the mind somewhere? Okay, good. It's actually just a version of the Pythagorean theorem, too, by the way, in case you've never heard that before. You actually know some of these values. x1, x2, y1, y2. What is it that you know? That 0.01 is one of the values in there, right? 2 of the values in there, actually. So the x value of 0 and the y value of 1 come from the fact that I'm trying to find the point closest to this particular point. That is one of the points in question. So let me write this one more time with that information sort of plugged in. So this is basically saying I need to take x minus 0, so that's the same as x squared. And then I need to take y minus 1 and square it. That's still not quite what I needed to have. What's wrong with the way it's written right now? It has an x and a y. How are we going to get rid of one of those? We're going to do a substitution. You're right, Allison. Do you know what we're going to substitute? That's okay. Allison's halfway there. We are going to substitute. What information on my screen have I actually not used in this equation so far? Yes, we are. There is a relationship between x and y that we need to use. It's right here. Y is equal to x squared. So in this equation that I've got for distance right here, I know that the distance, or that the y value is the same as an x squared value. So I'm going to substitute it, like Allison suggested, into the equation for y. So now I have the x squared at the beginning, plus, and now I have x squared minus 1 squared. Okay? We're good with that? Okay. I need to use calculus for this. I know that my distance needs to be less than 1. Obviously, my distance is greater than 0 as well over here. If you take a look at the x values in question, what can you tell me about the x value itself that we're looking at in terms of this particular picture? It's between -1 and 1, isn't it? Because anything we get further out from here is much further away, right? So the x values that I'm looking for are going to be between -1 and 1. And just realistically speaking, they look like they're going to be somewhere right in here, right? Those points, whatever those are, appear to be closer than 1 away. And those are the points that we're looking for. Okay, so let's actually go about finding that now. What do I need to do with this equation before I use calculus? Yeah, I need to simplify. Thank you, Mackenzie. All right, so let's simplify the inside of this square root, all right? So I have the square root, I have x squared. What happens when I take x squared minus 1 squared? X to the 4th is good, and then what? And minus 1. Okay, so we foil that out. Oh, plus 1, I'm sorry. Yes, you're right. Thank you. Plus 1. And then I can combine the x squared terms. So this actually ends up being the square root of x to the 4th minus x squared plus 1. And that's all the algebra for the moment. Now I'm ready for the calculus, right? What kind of rule am I going to need in order to take the derivative of this function? Chain rule, very good. Let me rewrite it one time. How else might be more helpful for this to be rewritten? To the 1/2 power, right? You don't actually have to rewrite it. You can just think it if you want to as you're processing through. That's okay. Either way, what do you get for the derivative of x to the 4th minus x squared plus 1 to the 1/2? 1/2. X to the 4th minus x squared plus 1. Good. Remember that exponent to the -1/2. What's next? You guys don't even realize how far you've come. That's good. Very well done. I think we should clean this up a little bit before we try anything else that's related to actually solving, right? Let's clean up what we've got so far. You might notice this is a -1/2 power, so -1/2 moves it back down to the denominator, right? The fact that it's a 1/2 means I could put a square root. So that part of my function, I'm going to rewrite like this. Okay, is everybody good with that? All right, the other thing I'd like for you to take notice of is that this 2 would technically go in the denominator, right, with the square root, and this piece would go in the numerator. But what can you tell me about the 2 orange pieces that are currently circled? You can divide them, right? You can simplify because they all have a factor of 2 in them. So we're going to divide them all by a factor of 2, which means I'm really going to have just 2x cubed minus x on top. It doesn't really hurt anything if a 2 is left in the denominator. It's not going to change anything in terms of your answer. This just makes it a little bit cleaner. That's all. Now what am I going to do now that it's all simplified pretty? Set it to 0. Now, setting this thing to 0 is equivalent to really doing what? Setting the numerator equal to 0, yeah. So let's look at the numerator. Set equal to 0. How am I going to find where this value's going to be equal to 0? Okay, I'm going to take out an x, actually. Factor out an x, which is going to leave me with 2x squared minus 1. Then what? Good. X is equal to 0. And? Either 2x squared is equal to 1 or 2x squared minus 1 is equal to 0. So x squared is 1/2, which means x is plus or minus square root 2 over 2. Right, the square root of 1/2 and then rationalize to square root 2 over 2. We are going to leave this in radical form. This problem is really not a very applicable problem with units and things like that, right? It's not application-based. It's a graph-based problem. Leaving it in exact form is the appropriate response. And so we're going to leave it that way. This actually gave me 3 values for critical values, didn't it? 1, and then here's 2, 3. This didn't really answer the question, but we actually do know that x equals 0 is not the right answer, or at least we expect it's not, right? Where is x equals 0 on this graph? It's the location of the bottom, not the graph. I don't mean like the picture totally. I mean the equation part. It's the minimum point of the vertex, right? That vertex location. Do you have a question, Daniel?
Yeah, in the last step, y is 2 over 2.
Why what?
So in the last step,
Yes.
it's 2 over 2.
It's square root 2 over 2. Right here, when we take a square root and you take the square root of 1/2, if you rationalize by multiplying top and bottom by square root of 2, that's where this bottom part comes from, yeah. All right, so we expect that the answer probably is that the x value is the square root 2 over 2 and the negative square root 2 over 2. That sort of looks like, from my picture, what I'm anticipating. How do I verify that with calculus? I either plug it into a second derivative, or I plug on into a number line from the first derivative. And to be honest, I don't really want to take a second derivative of this function. That one's really ugly, isn't it? I mean, I'm going to have quotient rule and a chain rule going on in the middle of it, and that doesn't look especially easy to do. So probably a sign chart on this one makes the most sense in terms of efficiency for the problem. So on my sign chart, what numbers are going to go in on my sign chart according to my critical numbers? Are those all of them, Josh? And 0. Don't forget the 0. We know 0 is not our answer, but it still will change the values that I pick around different things, so I want to be careful. All right, so negative square root 2 over 2, positive square root 2 over 2. What approximately is square root 2 over 2? About? About what? 0.7. It's roughly 0.7, right? That gives us some kind of an idea of what number we might want to plug in. So this is approximately 0.7. So I need a number that is smaller than negative 0.7. Negative 1 sounds fantastic. How about a number between that negative 0.7 and 0? Awesome. We'll do negative 0.5. Between 0 and square root 2 over 2, or 0.7? 0.5 looks good. And then greater than that value? 1. All right, and where are we plugging these values into? The first derivative. Very good. So this is f prime of negative 1. F prime of negative 0.5. F prime of 0.5. And f prime of 1. And I know you guys are already in the midst of doing this, but let me make you aware of something that you probably, I don't know, some of you might have caught it before or not. What is this denominator? Positive, negative, what is it? It's always positive, isn't it? So do I really need to plug any of these numbers into the denominator? I really don't, because the denominator is always positive. It's not going to change my sign at all. So I can simplify this problem really easily by only looking at what happens on this numerator. That doesn't happen with every denominator, but it does here. Why? Because it's a square root. And square roots are always positive values when we pull them out like that. Okay. All right, so what happens at negative 1? It's negative, okay? At negative 0.5? Positive. At 0.5? And at 1? Okay, so let me put those into my chart now. I had negative, positive, negative, positive. What does negative mean with the first derivative? It's decreasing. So I have 2 places where it's decreasing. And what does a positive mean? It's increasing. So somebody tell me what is happening at these particular locations. This one's a minimum, and this one's a minimum. If we had, for some reason, thought that 0 might give us something, what does this actually tell us about 0? It's actually a local maximum. Now, we know that the answer is not that it's an absolute maximum, because definitely, like, this point over here is further away, right? But it is a local maximum, and the local area around it is the biggest value away from it. All right, so we have found out that these particular points are, in fact, minimum points. Let's go back and make sure we answer the question as it was asked. What were we asked to find? Yeah, the point, and we found 2 of them, that's okay. The point. Have we actually found the point? Well, what have we only found the x value for it. We found 2 x values, right? Be careful, this is not the x and the y we found. That's not what we found. We found 2 x values. We found 2 coordinates that I need y values for. So one answer is negative square root 2 over 2 for x. The other one is positive square root 2 over 2 for x. How in the world am I going to find the y value? Yeah, we're going to plug it back in to this equation right here, right? This is how x and y are related. Y is x squared. So what happens when I square negative square root of 2 over 2? I get a positive. That's one thing I do. What else happens? It is 1/2. In fact, it might even be easier to go back to an earlier version of the square root. It's just square root of 1/2. What happens when I square root of 1/2? The square root goes away. And it happens for both of them, right? Same y values. So these are my 2 points that are the closest or nearest points on my graph y equal x squared to the point 0, 1. Any questions on that one? Now, the fact that we're actually using a specific equation and we're finding this related to a specific point makes it a little bit abstract. Like, this is sort of a mathy kind of question, right? But the idea of minimizing a distance to something is not a mathy kind of thing. That's what you guys do all the time when you drive somewhere, right? You pull up some kind of map on your phone, especially if you don't know where it is, and you try to minimize how long or how far, whatever it is, it takes to get there. And that's exactly what this problem is doing.